So I think I should start now. So last day, the last lecture, I used this construction, this observation. What is the rule of addition and multiplication in this field? So first of all, I showed that this is a field, and what is the significance of that field? This field will contain a root of px, where px is is an irreducible polynomial in fx, where px is an irreducible polynomial in fx, and this k is an extension of f. Actually, f not it is isomorphic to phi of f that we define. So if we identify f with its homomorphic image, okay, then it is an isomorphism. So as isomorphism does not change, actually k contains properly set theoretic contains phi f, but it is isomorphic to f. So k contains f in algebraic sense. So it is an extension and content if a root of px is equal to 0, and the multiplication roots are addition is simple, and the multiplication follows if the remainder. If you take two polynomial, divide by px, take the remainder, that will be the value of the polynomial, exactly the polynomial in k, because it is k. So equivalence class will absorb its representatives. Equivalence classes will absorb the correct elements, and the leftover will be r theta. That happens in every quotient ring, not only this ring. Okay, so today we will discuss some consequence of this, some example. I promised to do some example here, easy example. Examples. Correct some examples. First example, you already know, so let us start with some known example. Then Ex is irreducible in over R, and it is real number. Okay, so this is a field. Actually, who knows ring theory? I think you all knows ring. Exactly isomorphic to C as a ring. So it is a field. Both sides are field. But we will not use this thing. We will use our previous. We will use our previous previous theorem to observe the laws of multiplication here and addition here separately. Okay. So how it so obviously in the previous lecture I taught that elements of that quotient, whatever quotient you are taking, elements of this are polynomial with less than n, degree will be less than n, but here it is 2 degree, second degree polynomial. So they are only linear type of polynomial, less than degree 2. So the polynomial will be a plus bx bar type. Okay. So x bar is x, the equivalence classes of x. So obviously, so let us, so you don't, suppose you don't know what is this. So elements of k will be of the form a plus b x bar. Okay. Where x bar means x plus this thing. That means the ideal generated by this. Okay. I mean, it is not x plus, this is not like x square plus x plus 1. You understand, I think. Okay. Now, addition is trivial. Like if c plus dx bar is another polynomial in k, then their sum a plus bx bar that means what is the multiplication, right? What is the law of multiplication? Uh, multiplication what is this? For this we need to perform what is a plus bx originally and c plus dx in Rx. What is this? This is not natural multiplication. AC plus there will be x, so it is EC plus ADX, and now divided it with x square plus 1. Okay. Now what is the remainder? I mean, so what to be do? What to be done? This polynomial, it is originally in Rx, so there is no replacement here. It is fine till now. Now divide this by x square plus 1 and you will get a remainder. That remainder will be there. So what is the remainder? The okay, remainder. Let Rx correct? Qx be the quotient. Then obviously we have x square plus 1 into Qx plus BC plus AD x plus BB x square. Fine. Now do a trick. What is the trick? Put x square why we are doing so? Because in quotient x square plus 1 equal to 0. In the quotient, so it is this is 0 bar. That means that is same as this. So if we do perform this, what is Rx? And I will not put, see, I will put only the value of x square equal to minus 1. I don't know what is the value of x. But x square equal to 1 is guaranteed in the quotient. It is not in the original, it is in the k, okay? It is not in R. It is on inside k. So if we do this, what we are getting? We are getting that is 0. Rx will be Rx because there is no x square. Rx will be less than the degree of x square plus 1, so it will be linear. So AC x will be as there as PT into minus 1. That means AC minus PT plus AC. That is the remainder. Okay. That means so as what is the original image? So let only thing we need to do is sorry it will be okay. So only thing we need to do this in the so it is Rx. So in the what is Rx in the Rx bar that will be bar on X that is so Rx bar which we denoted by a plus bx bar. So it is AC minus BD. Scalar will be scalars and AD plus BC X bar. So that how we multiply two elements here. Okay. We took a plus bx, c plus dx, and their multiplication. So what is this? So multiplying the original thing and put x square plus 1 in 0. So put x square equal to minus 1. That will give you the answer. I think it is clear. For example 2. Okay. Now I can say from here. Now let me make an observation. Or now forget this. Who does not know can see that uh, multiplication then now can see addition is exactly like those. See if we replace x bar by I, which is equal to square root of minus. So that means how we multiply two things in C. Suppose I need to multiply 2 plus 3i with 1 plus I. So what do we do? 2 plus 3i plus 2i my, plus 3i square. Then I square plus 1 equal to 0. So I square equal to minus 1. So put I square equal to minus 1 here. So 2 plus 3i plus 2i minus 3. That will give me minus 1 plus 5i. Okay. That is exactly the thing we are doing. We are finding the, see, when we are finding the remainder, we did this. Put x square equal to minus 1. So now I can draw an isomorphism. Rx mod x square plus 1 to C I of a plus dx bar then goes to a plus bi and so it is okay. Second example will be more or less similar. See, sorry, take f equal to the ring operation, the field operation more generally, and ex equal to x cube minus 2. Okay. Then, sorry, first let me take x square minus 2, then I will go. Then it is irreducible over Q. So you can check by Eisenstein or you can check by Eisenstein or something like or root test. Because it is degree 2 polynomial, so if it has a root, it is reducible over Q, then it must have a root. I mean, the root test is valid for only degree 2 and 3, it is degree 2, so it is valid. So anyway, that is up to you how you will test. That is not the fact. So what is fx by my what is fx by ideal generated by qx will look like, and what is the multiplication? So addition. So what is the degree of extension first of all? If k equal to qx mod x square minus 2, then k column f is 2. Because It is exactly the degree of the irreducible polynomial. In the previous day, we have proved this. It is exactly the degree of the irreducible polynomial. So it is second degree. So it is the degree of extension is 2. And third is this is K over, that is the thing. So how the multiplication looks like? Sorry. Sorry for my poor English. Pardon. How does the multiplication look like in K? So we take any two elements. Let A plus bx bar. So that is AC plus AD plus BCx bar plus BD x bar. Now we have in the quotient x cube in K. Quotient is the K here. That is K that that ideal, the equivalence class is equivalent to 0 bar. Okay, that is x bar square equal to 2. So you can put there directly. Put there. Have a product. Just a minute. Just a minute. So it is 2 bar. If we replace there, I am directly writing product as AC plus AD plus BC x bar plus BD into 2. AC plus 2BD. That is the multiplication. Okay. And that is also obtained by remainder thing. That will be the remainder. That will be the remainder here. So then this is 2 equivalent to 2. That is not a serious issue. That is 0. Okay. So one can also show that A is isomorphic to Q square root of 2 by defining A plus bx bar goes to A plus b root. Okay. Now a bit of different thing. Okay. Suppose Px is of the form A0. I's are coming from F. Then what is X bar inverse? That is a question in the quotient field. Okay. So observe that. So inverse is unique. Okay. So in K, the image of this is 0. That means S0. That is same as 0 or 0 bar or is minus A0. So take common. Take this common. X common. Take the X common here. X bar A1 and take A0. Okay. So we are considering A0 is 24%. If A0 not equal to 0, then if A0 is equal to 0, then it is reducible. Okay. Reducible. Okay. Now it is non-zero, so inverse, take this there. x bar into minus 1 by a0 that will give you 1. Okay, 1 means 1 bar. Why I'm not writing? Everything is loaded on bar. So inverse that is the inverse. Okay. Example 4 in so we need to calculate the inverse of 1 plus x bar. Right. So it is degree 3 irreducible polynomial. So the quotient field will have degree n polynomials, degree third degree polynomial. So let a plus bx bar that much. 1. That means a plus ax bar plus bx bar plus bx bar square plus cx bar square plus cx. That implies but x cube equal to 2. So I need to put here. There is the sketch. Now compare coefficient. We will get a plus 2c by 1. And other things are 0. A plus b 0. D plus c. So from these two, I get that a equal to c and 3c equal to 1 implies a equal to c equal to 1 by 3 and b equal to minus 1 by 3. So the required inverse is what? 1 by 3, 1 plus, sorry, minus x bar plus x square bar. X square bar you can write is also x bar square. They're the same thing. No problem. So I think the rule will be key here. Yeah. Just see this. Just 1 minute break. I will start after 1 or 1.5 minutes. Okay. So I hope you understood these things. So actually you can put everywhere bar because everything in this thing is equivalence, some lies in some equivalence class. So if you wish to put here bar, put everywhere bar, no problem. One is there, one bar also. So it is fine to put here bar. That is not, but you need to put everywhere then. AC bar, 2 BD bar, AD bar, BC bar. Actually, what is the fact that the constant, the constant elements forms their own equivalence classes. Suppose one bar and two bar. Okay, they are separate classes. They never intersect. So one and one bar, they will not. I mean, in we are making it quotient by a polynomial of some higher degree. So constant term will not fall in some same equivalence class. So one and one bar are same, but obviously, suppose Q1x and Q2x, they might not be same because their difference they might be unequal, but their difference might fall there. For example, x square and 2. They are different, but their difference falls there. But 1 and 2, so if you can omit the bar, if you can remove the bar, that will not make any difference there. Because they are already in separate. They will always remain in same, other different equivalence classes. Okay, no problem. You can then put it there. If anything is fine, no problem. So we will now move towards two definitions here. Definition. Let A over F be a field extension and suppose alpha 1, alpha 2, alpha 3, alpha n set in K, then the smallest subfield of K suppose this is S is denoted by so it is the smallest field. For example, you might have an ambiguity now. What is the ambiguity? So for example, uh, suppose root 2. Root 2 does not belongs to Q. So what is the smallest field? So what is the smallest field? What is Q and root 2? So anyone might think the answer is R. Anyone might think C. But they are obviously fields, but not smallest. So to get the smallest one, do one thing. To get the what is the smallest subfield, you will do. Oh, then the thing is Q root 2. It is the smallest one. How? Take Q, attach the missing element, that will give you the smallest. And you can also verify. You can also verify. Why? Let me verify step by step. Don't worry. Let K1 be any field, any subfield of K that contains both, sorry, else that means K1, sorry, that is K, K1 that is F, that is smallest thing. So what do we show? That any subfield that property satisfies this property K1, th- that will that contains this thing. So this is the smallest thing. I cannot drop this. If I take anything, then that thing will come into this. So let us prove this. So K1 contains this. So then K1 automatically, it is, I mean, it is an observation, right? It is not even a theorem. K1 contains every fraction of, I mean, every element. So let me erase this. That is trivial thing. I can, I mean, even given a hint. That is because I am including elements. So what is, if I ask you, what is the smallest ring that contains, sorry, what is the smallest ring R? What is the smallest ring? Suppose R is a ring, X is a variable, R is a ring and X is a variable, then what is the smallest ring contains both R and X? So the answer is obviously Rx. Why? It contains R, so the ring contains all the scalars. It contains X, so X means, sorry, the set. Consider the set X, X square, X cube, dot 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 dot. So X will be there, so X square will be there. So it is a ring. So X plus X square will be there. So and X plus X square plus X cube, all things will be there. So R and X are there. So it is a ring. The ring satisfies addition. So element of R plus X. That is 1 plus X, 2 plus X, 5 plus X square. Everything is there. But we are constructing Rx. Let's see. Same way, what is the field? So take any element of F and attach an element of alpha, polynomial. It is a finite polynomial in this thing. So you attach, take the quotient. So what we are getting? We are getting these things. I think you are getting the intention. Okay? Why it is the smallest? I cannot go down. I have to have this thing. Okay. So see, if I am saying that what is any field containing F and F, in that example, what is any ring containing R and X? There are many examples. For example, Rx, R, X, Y, R, X, Y, Z. So many more. But what is the smallest? That is the unique one. And that is this thing. That is this thing. So I will write it in the same definition. If the field K equal to FA. Oh, sorry. And is called generated by alpha 1, alpha 2 over base fit. F is called the base fit. So in particular, if then, so it is generated by some simple element. For example, q root 2 over q. That is a field. Q root 3, root 2 comma root 3 over q. That is another field. But if that type of condition happens, then it is called a simple extension. Simple. So it is analogous to cyclic. Cyclic means it is generated by a single element. It is not generated by a single element. I mean, it is generated by, I mean, only one single element. So group generating set and field generating set, in this context, they are different. So there is one alpha, alpha square, that type of things will be there. Yeah, you can say that is the same thing, obviously. No ambiguity. And alpha is said to have a, and alpha is called a primitive element. For example, it's not simple. Extension. C over R is not simple. Oh, sorry, it's simple. Why it is simple? We can write. What is C? Is this thing. We are learning only one element. R over Q is not simple because this is not simple. Okay, let me make it simpler. Let us write Q pi comma. Because you cannot punch the two element and take it in a simple thing. Okay. So you understood the concept of simple extensions here. Now, a small theorem that you have already checked or already known. So that you have already guessed, I think. What is the theorem? So I remember in few theorems ago, I told that if Px is a is a irreducible polynomial over f, if Px is irreducible polynomial over f, then k equal to fx mod Px is a field and field extension and contains a root of f. So in proving that theorem, so in general I am saying what I am trying to say. So in general, what I am trying to say, I am explaining. The previous lecture. Sorry. There is a field extension. So I told you the field extension is this. So you might frighten what is this type of field. So I convinced you forcefully that this is a field and I will later describe a simpler figure of the field. Next theorem is this. What is this field actually looks like? You already guessed. That is actually if that is a simple extension, if alpha. So this is much better looking field than this. This is actually isomorphic. I will put the isomorphism in this theorem, basically. So let me write the statement formally first.